back to where I had the example of the percent ionic character equation. You would look up the electronegativity values on your periodic table and just substitute those in. Maybe your teacher is even nice enough to provide you the electronegativity values in the problem. Then all you have to do is find the difference, divide by the bigger one, times 100, pretty simple. If you are really observant, you might also realize that you can answer the problem without doing the math if you look at the kinds of elements that are bonded. So, know your differences between metals, metalloids, and nonmetals, and the type of bonding that those substances typically undergo. Moving on to test question number 6, which is hint 36. Identify the number of electrons that must be shown in the Lewis structure of a given polyatomic ion. Well, elements are trying to fill up their octet, okay? And everybody except hydrogen, which we know can only hold 2 valence electrons. So, regardless of what polyatomic ion it might be, look for the fact that atoms are trying to fill their outer shell, especially if they're nonmetals. Polyatomic ions, even though they are ions, actually are made of nonmetals and are covalently bonded. They're sharing valence electrons, yet end up with an overall charge. So, how many electrons? Well, they're going to get 8, unless it's hydrogen, and then it'll have 2. Test question number 7, which is hint 37, define formula unit. I shouldn't have to give you much help in a video or otherwise when it comes to a definition question. You can look up definitions. Those are the kinds of things that are great background information for you to have in your hip pocket or in your brain when you're doing an honors page. A formula unit is like a molecule, but it applies to an ionically bonded compound. So technically that's the name of the smallest little bit of an ionic compound. We know that they don't exist that way individually, like we don't have one atom of Na with one atom of Cl that builds up in a crystal structure. We'll get to that in a little bit too. But it's just another, it's like a molecule, okay? Just another name. Test hint number 38, which is question number 8. Describe the ion arrangement in a given ionic crystalline solid. Okay, well, here's our, I don't know how old it is, styrofoam model of a sodium chloride crystal. I'm guessing it's pretty old because these white styrofoam spheres are pretty grungy and it's really kind of gross. But we're alternating here. The red spheres are the sodium ions, and the white spheres, the bigger ones, are the chloride ions. Chloride is bigger because it has gained valence electron and filled up its outer shell. Fewer protons than electrons, so we know from our trend in the periodic table chapter, those anions are going to be bigger. Cations are going to be smaller because they've lost that outer shell and there's more pull on the remaining electrons from the nucleus. We have to build up these crystals with opposite charges. Okay? It has to alternate, positive, negative, positive, negative. If we put all the negatives on one side and all the positives on the other side, they just push each other apart. They would repel because of the electrostatic charge being the same. Has to be different and alternate in order for that crystal to hold together. So, if we looked at a crystal like this example of NaCl, which is typically the example that's used, if I look at any given chlorine, around it there are going to be 6 sodium ions. Top, bottom, left, right, front, back. Same thing with a sodium ion. It is going to be surrounded by 6 oppositely charged ions. Remember, when something becomes charged, it's not just charged on one side, it's charged all the way around. Above, below, left, right, my left, right, front, back, and the ions are going to attract from every direction. Okay, moving on to question number 9, which is test hint 39. Describe the interaction between valence electrons in adjacent ions. Valence electrons in adjacent ions. Now, electrons are negative. Negative charged particles are going to want to repel each other. The reason the ions are attracting is because they end up with a net charge due to different numbers of valence electrons. So think carefully about this question when you answer. Read it carefully to make sure you understand what this question is truly asking. That's all the hint I'm going to give you for right now. Question number 10, which is test hint 40. Describe the state of energy in an ionic crystalline solid. Okay, well, when these ions bond and attract each other, a lot of energy is released. You know that from your investigations of the Born-Haber cycle. Energy released in a chemical system means it's going to a more stable state. So they end up at a state of least or minimum potential energy. That makes the arrangement of atoms stable, it makes the compound more stable. It's the tendency we see in nature, and we talked about that way back at the beginning of the year in chapter 2. Okay? So atoms, when they bond, are going to go to a state of minimum potential energy. Test question number 11, which is test hint 41. Compare the strength and lattice energies of two compounds. Okay, so make sure you understand what a lattice is. I'm glad I remembered to get out my sodium chloride crystal here today. Sodium chloride is an example of a lattice structure. I have a couple different documents posted on Moodle to compare different kinds of ionic crystals. You have several examples in your book to take a look at, and we've been giving you video examples of things as well. Take a look at the pencast too. This builds up a lattice, not lettuce, it's not going in a salad, but the alternating charges create these patterns, rows of alternatingly charged ions and so on, or alternating ions. This is a crystal lattice structure. Well, if the lattice energy, the energy holding this crystal together, is greater than holding some other crystal together, which I don't have another model of that, so you'll have to kind of envision one, then what can we say about compound A compared to compound B? Well, the stronger the lattice energy, the stronger the bond, the stronger the attraction between the ions. So if we're comparing one to something that has a lower lattice energy, we don't have to have quite as much energy to melt the substance and break the bonds. That would be a weaker, more weakly bonded compound. And this question is just really very general when it's comparing substance A and B. Moving right along to test question 12, which is test